If you haven't heard about large language models before, I'm sure you made a very diligent attempt to not follow any news or read anything on the internet or anywhere else, because they've really taken over the world. So in this video, I'm going to talk a little bit about how they work on the inside. Large language models, of course, now we really associate that with GPT or ChatGPT. I'll actually outsource my high-level introduction of large language models and give that to an expert. So Andre Karpathy has a really nice video. It's an hour long, but it's really worth the watch. And I say it's high level, but that's not actually entirely true. It actually goes into quite a lot of depth about what happens under the hood with these large language models. So I'll put a link in the video description. Go and watch that first. And my intention is to give a little bit more of the details that he missed out on in that video. GPT is just a transformer language model. So a language model is basically a model that tells us the probability of some word occurring given previous things that happened, previous words that occurred. That's a language model. A transformer, go and watch my transformer videos. They're a type of neural network that works with attention. And GPT is just predicting one word at a time, one after the other. It's a very big model, but here I'm just going to draw and pretend that it just consists of two transformer layers. So you've got transformer layer 1 and transformer layer 2. And I'm quickly going to explain what happens at inference time, at test time when you're using the model. So if the model has already produced two words, it looks, after starting a sentence or starting an answer, it's now going to ask what's the next word that I should output. And basically these vectors in the first transformer layer are going to be produced by using self-attention from the inputs here. And then these vectors will be produced by doing self-attention on the vectors here. And then you're going to get an output vector here. And this is going to be a big vector, maybe a few thousand dimensions over the possible output words. Okay. And then we're going to say, okay, in some way, you're going to select one of these output tokens by sampling from this distribution. There's multiple ways in which you can do that. You can maybe just take the max and say, what is for the element corresponding to the max here, what is the associated word? And I will output that. Or you can do something more clever, which is definitely what GPT is doing. So you can sample probabilistically from this output distribution, basically roll a 1,000 sided dice and see with the sides weighed according to the output probabilities, and then see which one comes up heads. And that's the thing that you output. GPT probably does something even a little bit more fancy than that. But that's the basic principle. And what it will then do is it will say, okay, cool, we sample, and let's just pretend that it samples the word like. Okay. And that's then the word that it outputs at this time step. And then what it will do is it will say, okay, cool, now calculate this vector here by doing self-attention on all of these inputs. Okay. So let me go into a little bit of detail on how that happens. So for each of these input vectors, you're going to calculate a key and a value vector and a query vector. Okay. And you're going to do this for each of these vectors. So you'll have key, value, and each one will have a query as well. But just when we're looking at this time step, we don't care about these queries. And then what you're going to do is you're going to take the query vector and you're going to do the dot product with this one's key, this one's key, this one's key, this one's key. And then you're going to do, so each of those gives you an attention score. You push those through a softmax that gives you attention weight, and you take the weighted sum of the value vectors for these. Go and watch the attention videos if that doesn't make sense. So this red vector goes in there, this red vector goes in there, this red vector goes in there, weighted sum, and that gives you the hidden representation in the first transformer layer at the fourth time step. And then the same thing happens here. So here again, you're going to do a weighted sum over all of these from the first layer. Okay, so we now have the hidden representation at the fourth time step in the second transformer layer. Then what we'll do is, from this we'll get the output distribution, but that probably means we pass it through some little block, maybe a little transformation that actually sits there and there and there and there. And that gives us a big vector here, again a few thousand dimensions big. This one is y hat 4. Okay, and then from that one, again, we take that vector, we pass it into a sample block, we take the output word, let's say it's the word you, and that's the word that we then feed into the next time step. Pretend that those lines are straight. Okay, so we take you, and again, we calculate key value query, and we go on in this way. Okay, and we continue in this way. We sample another word, see if my lines are straight at this time, feed it into the next time step, and so on. And we do that until we sample a special token that tells us we're now at the end of the sentence. I write end of sentence here, but in a later slide I will show you that it's probably more something like end of answer, because the model needs to produce an answer. If it's GPT trained as an assistant, like with ChatGPT, then it will output stuff until the little special answer token is produced. And I just use end of sentence for now. So this is at inference time. It's a little bit crazy to think that this thing that has really shaken the world is just producing one word at a time, word by word, and feeding that back into itself. It's important to just say that when a model takes its own output as its input at the next time step, we normally call that an auto-regressive model. So at training time, we don't have to produce one word at a time, because we basically scrape some text from the internet and we know what the next words are, so we don't have to feed them back in. And we can directly calculate a loss that tells us how good are we at predicting the next word. So if we just for now just look at, for example, the fourth time step here. So let's just look at what happens at the time step when the input is like, and the word that we're trying to predict, the target, is you. So at this fourth time step, our model outputs a y4, which is this big vector. Like I said before, it's maybe a few thousand dimensions big. And what we're going to do is we're going to have a little loss term that tells us how big is the probability that's placed at the word you. Okay, and that's when we train it with a negative log likelihood. We're basically going to take the cross entropy between this vector here and a one-out vector representing the word you, and that is going to give us our error term for the fourth time step. Okay, this is just like a normal language model. Now, the important thing when you use transformers is that you can't actually look into the future when you're doing this. Okay, and so let me just explain this in a little bit more detail. One option is to say, well, when we're calculating this fourth hidden representation in the second transformer layer, we take, like usual, we take the weighted sum of this, 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 and this. Okay, and we take the weighted sum of all of those things when we're calculating this vector here. But this is really problematic, because this means the model can actually essentially cheat when it's doing that. How does that happen? Well, this hidden representation here, this one will be based on all of these vectors, for example, that one, and that one. And now what happens is when we're calculating this hidden representation here, it actually knows what word is coming next. In other words, the model can cheat. It can use its hidden representations to tell this time step, listen, place a lot of mass at the dimension corresponding to the word hue. This is very different from what happens at inference time, right? At inference time, the model is predicting one word at a time. And so when we're at this fourth time step and it's asking what should happen next, the model has no idea what the following words are, right? Because it's predicting it one at a time. At training time, of course, we've scraped some text, so we actually have the whole sentence, and we can, in principle, if we want, we can look into the future, but that doesn't match what's going to happen at inference time. And so it's important to actually deal with this and to make sure that what happens at training time matches what happens at test time. And the way to deal with this is something that we've looked at in a previous video. It's called masking. So the idea of masking is basically to constrain the attention weights so that when we're trying to predict, for example, the fourth time step in this example here, that it's not allowed to look into the future. Or more concretely, it's not allowed to incorporate the values of things that happen into the future when it's calculating the representation for this time step here. And how it does that mathematically is it puts a attention score of negative infinity for all the time steps that follow, which means that the attention weights are 0 for those time steps. And that means that when you're calculating, in this case, the fourth representation here, you're not going to incorporate any of the things that happen in the future. Now, large language models do exactly the same thing. And that means that if we're calculating the hidden representation here, we're actually not going to weigh these things that happen in the future as well. These things will be masked out, which means that for this fourth time step vector here, we consider all of these as not existing, basically having 0 attention weights on them. So all of these are masked out. And that really means that what happens at training time matches what happens at test time, at inference time. But at training time, we know what words should come next, which means that we can parallelize this thing. One of the major benefits of using transformer language modeling. A few extra things to mention here is that what I've described here is sometimes called a decoder-only model. It doesn't have an encoder and a decoder, right? It's just one model that's auto-regressively producing its output at test time. And another thing to mention here is in the little examples that I've given, I've used words as the input units here, but the model probably uses some subword units like byte pair encoding, BPE units. Have a look at my video on BPE if you want to know what that is. So then the major question is, if this thing is just, in quotes, a large language model, just a language model, what is the difference of something like GPT with what came before it, with the language models that preceded it? And the answer to this question is, there's a number of things, but the two big things is the size of the model. It definitely has more than 2 layers, and the number of parameters in each layer is very, very big. So GPT is just a massive, massive model. And then the second thing is the size of the data on which it's trained on. The Andrej Karpathy video mentions that it's almost like compressing the whole of the internet into the model weights. Basically, you have scraped all the text that exists and you're plugging that or compressing that into a model by trying to predict the words that follows. And these two things, size of model, size of data, is really what enabled GPT to be one of the best models out there. I should probably mention that GPT stands for Generative Pre-trained Transformer. Is that right? Okay, I checked. It is right. So it's a transformer and it's generative because it's predicting the next time step. And the pre-training part I will actually explain right now.